Okay, so in this discussion, I'm going to go over building envelope and talk about heat transfer through a substance. So this is something that we'll deal with a lot in this course because a lot of heat gain and heat loss is through the building envelope or the outsides of the building. Okay, and so we'll actually learn how to do the calculation as well. So first of all, some terminology you want to jot down: a building envelope. So the envelope is the area of the building or the portion of the building that encloses the conditioned space. You want to jot down that term, conditioned space. So the conditioned space is just the area of the building that's actively heated and cooled. And so something like an unconditioned basement, you're not actively heating and cooling that, or an attic space like up here that you're not actively heating and cooling, that is not part of the conditioned space. So the building envelope in this image, because the attic is unconditioned, okay, so here's your envelope. Even though you have this part of the roof, that's actually not part of the envelope. The envelope would be here where the insulation is, that encloses all of this conditioned space. So in this image, the basement is conditioned, and so whatever the foundation and floors are made of and the walls are made of is part of the building envelope, right? So here's another example. If you look at this house, the building envelope encloses the conditioned space, and the building shell just is it delineates the inside and outside of the building, right? So the building shell is easy to figure out. The building shell is just the exterior of the building. The building envelope can be a little more tricky, and we spend a lot of time in energy management figuring out where the building envelope is. And sometimes we can sort of manipulate the building envelope in some different ways. So first of all, let's look at this image. So where's the building shell? So feel free to press pause. So the shell is pretty clear. It's the outside of the building. Okay, so that's outlined in red here. What about the building envelope? So this one's a little trickier, but from the looks of it, remember, we're enclosing the conditioned space. From the looks of it, it's here. This basement looks unconditioned because of the bare concrete. It's not uncommon to have your hot water heater and laundry in an unfinished basement, so it just depends if it's finished or not. But it looks unfinished to me, which would mean that this would be our conditioned space. Okay. So I'm not, you'll actually hear sometimes people out in the field will refer to the envelope and the shell as the same thing, but really it's not. The shell is what contains the inside and the outside of the house, but the envelope is what we're really mostly concerned with when we deal with energy efficiency and the energy systems in a building, and because we spend a lot of time conditioning the space, a lot of money and energy conditioning the space, and so it's really important to understand where this building envelope is. So real basic aspect of thermodynamics. We've gone over the first law of thermodynamics, which is that energy is not created or destroyed. The second law, which really is that the entropy of the universe is always increasing. You don't need to know that part. From a practical perspective, what this means is that nothing is 100% efficient. Okay, so no energy conversion is 100% efficient. So when we use a furnace, it's impossible for that to be 100% efficient. There's always some waste. Some of the energy, goes out in the form of gas or carbon, unburnt carbon, and so forth. So nothing is 100% efficient directly. The second aspect that's important is that heat always travels from warmer to colder areas. So this is really important. Number one, there's no such thing as 100% efficient. So there's always less than 100% efficiency when you convert one form of energy to another. We'll deal a lot with this today, and that is that heat always travels from warmer to colder areas. Now you can force heat to move in the other direction, but that uses energy, right? And so left to its own devices, let's like you have two areas. You have a warm side of a wall and a cold side of the wall. The heat's always going to travel from warm to the cold, right? So like a window that's hot outside, cold inside. Excuse me, the heat's going to travel from outside to inside, and then vice versa if it's the opposite. Okay? So that's based on thermodynamics. It's something you can't help or you can't change. So in this quick example here, we have an example of a home in a winter and the summer, right? You can see it's 70 degrees inside for both. In the winter, 10 degrees outside, and it's 90 degrees outside in the summer. Not super unusual. And so, important thing to jot down is delta T. This term delta T, which we'll use a lot, that just means temperature difference. So delta means difference. So delta T is temperature difference. So here it's 70 degrees inside, 10 degrees outside. Our delta T is 60, right? 70 minus 10 is 60. Easy. Here, 90 outside, 70 inside. Our delta T is 20. Okay? So what's the point? The point is the higher your delta, all else being equal, the more heat is going to flow through the surface. Okay? So let's look at this example. So in the winter, we have it's warm inside, cold outside. So what direction is the heat going to flow? It's going to push out, right? It's going to try to travel through the ceiling, through the floor, through the wall, because it's higher temperature inside than it is outside. That's something, again, you cannot change. Heat will always try to move from higher to lower. Whereas in the summer, you can see it's warmer outside, and so you're going to have heat that's trying to get through, that is traveling through the walls, through the ceiling, and so forth. You notice the arrows are bigger here on the left than the right. That's because the delta is much bigger, right? So we have 3 times the delta, which means all else being equal, 3 times the heat is going to, or heat's going to go through the wall and other surfaces more quickly. And actually 3 times as quickly, okay, or 3 times as much. And so remember, flow is always from hot to cold, and higher delta means more heat want to enter and escape the building, and also air to a lesser extent, but today we're dealing with heat. So remember, heat conducts from warmer to colder sides. Always goes from warmer to colder. There's really nothing you can do. And we can actually measure the rate of heat flow. And that's what U value and R value are. Really, U value is the one that's the true measure of heat flow. So we'll start with that. So you want to jot this down. U value is how much heat in BTU flows through 1 foot slab of material, 1 square foot, every hour when there's a 1 degree temperature difference on either side. And the units are BTUs per square feet per degree Fahrenheit per hour, which should make sense. So U value is a measure of transmittance. It's a measure of transmittance, how much heat is transmitted. So you want less transmittance, all else being equal, right? Like you want to have good insulation. That means lower transmittance. So smaller is better, okay? Smaller is better. And let's go over a quick example here. So if you look in a typical attic space in a house, you should have about 18 inches of fiberglass bat, or 18 inches of insulation. It could be blown-in insulation. Okay, so if you have 3.5 inches, like if you have the wood joists that are 3.5 inches, you're going to have less insulation there. So let's just say that you filled in the insulation in between the joists, but then you leave the bare wood there, right? And so that 18-inch thick insulation is going to have a U value of about 0.018. These are approximate numbers. It depends on a few factors. The wood's going to have a U value of about 0.28. Okay, that really doesn't probably make a lot of sense. So let's look at the implications of this, right? So let's look if we have 1 square foot of each, and it's 70 degrees on one side and 69 degrees. So just a 1 degree temperature difference on either side of that ceiling, okay? So that's a delta T of 1 degree. So let's look at the heat transfer, right? So I have 1 square foot, and there's a 1 degree of temperature difference. And so that, by definition, means every hour with the fiberglass, it's 0.018 BTUs per hour, right? So remember, how many BTUs for a 1 square foot when there's a 1 degree temperature difference each hour? So each hour, we're going to lose 0.018 BTUs through the fiberglass. And we're going to lose about 0.28 BTUs per hour through the wood. That's almost completely inconsequential. So let's sort of step things up and get more realistic here. So what if I have 1,000 square feet of each, and just that 1 degree temperature difference? So now, if you have 18 0.018 BTUs per square foot, and I have 1,000 square feet, that means if I have 1,000 square feet, it's 18 BTUs per hour. And then the same principle applies to the wood. It's 0.28 BTUs per hour per square foot. So 1,000 square feet, and we're up to 280 BTUs per hour. So now we're kind of getting to a more significant difference. But what if, I mean, this is pretty rare that we just have a 1 degree temperature difference. So what if we have a bigger temperature difference? So let's say we have a delta T of 50. So now we have 1,000 square feet and a delta T of 50. So now we go from 18 BTUs per hour, and that's per degree Fahrenheit here. And so if we have 50 degrees Fahrenheit, it's 50 times as big. So our heat loss through the insulation is going to be about 900 BTUs per hour. And through the wood, it's about 14,000. So now we're really having a significant difference. But this is only for 1 hour. What if we're, for just part of, most of a week, we have this 50 degree temperature difference? So let's say we have 100 hours of these conditions, right? So now we have a 50 degree difference with 1,000 square feet for 100 hours, which is less than a week. Okay, so not unusual during warm or cold months, especially cold months. And so now we have 900 BTUs per hour for 100 hours, and that's 90,000 BTUs, and then 14,000 BTUs per hour for 100 hours is 1.4 million. So now you can see how this really starts to add up, and then you have all these other surfaces. You have the ceiling, you have the walls, you have the floor, you have everything else, and that heat loss can really add up, even though we break it down to the U factor, and it's like, wow, 0.018, 0.28, that doesn't really seem to make much of a difference, but as you can see, it does add up once you start scaling up. And one of the important take-home lessons here is that heat transmission, all else being equal, it's going to increase with increased U. So a higher U means more heat movement, increased area, and increased delta T. And I would add increased time as well. Okay. So that's the basics of U value. So let's look at how that's related to R value. So remember, U value is a measure of transmittance, and smaller is better. R value, on the other hand, is a measure of resistance. So bigger is better. All else being equal, you want to have a higher R value, right? So in this image, you have the gentleman looks like he's installing R38. That's going to be about twice as good as R14, right? And so we want to go, normally in an attic, we want to have about R48. But anyway, R value is, as it increases, it means you're more resistant to heat flow. Okay, so it's based on the type and the thickness, right? So everything has an R value, everything has a U value. Just you can find it somewhere, right? So like a window has an R and a U, insulation has an R and a U, even like your skin and the shirt that I have has an R value and a U value. You can find an R value or a U value of anything. It's just a property of the material. Depends on how much it allows heat to travel through it. It's really, really important to remember that R values are really easy to use because they can be added, right? So if I have R11 and R38, and I have an R11, right, and then I add R38 on top, just add it. Then I end up with R49, okay? I'll talk about how to convert that to a U factor, but R's, just write that down. You can add R values. And I'll just briefly go into how insulation prevents heat movement or reduces heat movement here. And it's really all about air pockets. This is just kind of an FYI. We'll go over different types of insulation later. But this image on the left is an electron microscope scan, close-up scan of fiberglass insulation. And here's a spray foam insulation close-up. And so briefly, here's how this prevents heat flow. So if heat is trying to go, let's say, from this side to this side through the insulation, what's going to happen is the heat's going to go here, it's going to hit this, and then it's going to have to warm this up through conduction, right? So then this little fiber is going to warm up, which doesn't readily warm up, by the way, because it's extruded glass, right? So this slowly warms up. And then what happens? You're going to have some heat eventually that goes out as radiation. You're going to have some heat, believe it or not, inside these little tiny air pockets, there's going to be some convection in there as well, right? and then slowly it'll make its way over through conduction if it's touching, right? So in order just for the heat to travel from this side of the pocket to this side of the pocket, a lot has to happen. This has to warm up, it has to radiate, it has to convect, and then has to come over here, and then eventually this starts warming up, right? Okay, and then eventually that's going to radiate, it's going to convect, it's going to conduct, and you're going to go over here, right? And so all these little tiny air pockets, they're just presenting barriers to the heat flowing through, and that's how insulation works. It's all about the air pockets. Okay, so you have like, think of like a solid piece of metal. The pockets are just minuscule. If there are any air pockets at all, they're minuscule. So that heat, if this was a close up of metal, it would be solid material and it would just conduct right through, right? So heat or metal is a really good conductor, whereas insulation is not, and it's all because of the air pockets, and the air pockets just prevent heat flow. And it's the same here, right? So this air pocket, it has to conduct and radiate through there, and then conduct and radiate through there, conduct and radiate through there, and so on and so on and so on. So more air pockets and less conductive material, the better. Okay? So that's basically how it works. Okay. And so there's something that's really common in buildings called thermal bridging. So you want to just jot down the term thermal bridging. And that's just where conductive heat transfer facilitates heat loss more quickly through certain building components. So if you look at this image here of a building, you can clearly see the studs, right? So this is a thermal camera picture of a building on a cold day. And so the warmer areas are where there's more heat conducting through the walls. And there's more heat conducting through here because it's wood or metal, right? Whereas the insulation pockets, you can see there's actually less. It's colder outside, okay? So it's colder outside where the insulation is because there's less heat loss. Whereas you have some thermal bridging that's happening where the studs are. And so a really good example of this, if it's a really cold day outside and you put your hand on an outdoor doorknob and the doorknob's really cold, that's because that doorknob is made of metal and goes right through the doorway, and it actually more readily conducts heat. So it conducts the heat out and it's cold, whereas the door has some insulation in it. It's made of material that holds the heat in. Okay, so that's thermal bridging. So again, R values can be added, U values cannot be added. So that's really important. U values cannot, let me circle that. U values cannot be added, but R values can. The other thing that's important to remember is this basic relationship here, that R is 1 over U and U is 1 over R. Pretty easy to remember, okay? So to find U, you divide 1. To find U, you divide 1 by R. To find R, you divide 1 by U. Okay? So let's go look at a quick example here. So if I have the following layers, if I want to calculate the R value and U the value, it's pretty easy, right? So imagine just 3 layers on top of each other, R1, R2.5, and R3.5. So the total R value there, super easy. Just add the 3, it's R7. How do you find the U value? 1 divided by 7. Okay, so my U value is going to be 0.143. It's really that easy. So once you have multiple any number of surfaces, you can add them up, get the R value, and then invert that, and you get the U value. Okay? Just as an FYI, just to show you why adding U values doesn't work, let's first convert these 3 R values into U values, right? So we have these 3 surfaces, and we have 3 different R values. So let's convert them to U's, add them up, and see what happens, right? So if we convert each of these to U values, we get 1, 0.4, and 0.286, right? Like 1 divided by 1, 1 divided by 2.5, 1 divided by 3.5, okay? So we get those 3 U values for those 3 surfaces. So if we add them up, we get 1.69, whereas the correct U value is actually 0.143. So you can see that actually gives us a factor of 10 higher U value than is accurate, which means if we added the U values, we're going to be really wrong. That's the short story. So never ever add U values. Okay? To find the U value, you always add the R values together first and then find the U. Okay, and we'll get practice on this in lab. And then lastly, how do you calculate the heat loss through a surface? There's a really simple formula. Heat loss is UA delta T. So U factor times the area in square foot times the temperature difference. That's it. Okay? So let's look at a quick example. So if I want to calculate the heat loss, we have 100 square feet of surface. That's a U value of 0.143. The temperature difference is 10 degrees Fahrenheit. What do? Just plug and play. U A delta T. U times A times delta T, we get 143 BTUs per hour. What if we have the same surface, but it's a 20 degree delta? Again, UA delta T. UA delta T, 286 BTUs per hour. What if it's 20 degrees and 200 square feet? So now it's U, same U, times 200 times 20, 572. What if the delta is 20? And what if we increase the U to 286? What's the heat loss going to be? Again, just UA delta T. 0.286, 200 times 20. Again, the heat loss is going to go up. Right, so this formula is used all the time in building science. And this is something that we will use in class and get some practice with. And again, just as a general rule, heat transmission is going to increase with increased U, increased area, and increased delta T. Okay, so that was a lot, so let's summarize. So number one, remember the building envelope encloses the conditioned space. Okay, so building shell is just the outside of the building. Building envelope is what we're really concerned with. So U value is a measure of heat transmittance or transmission. Smaller U is better. R value is a measure of resistance, and you want a bigger R value. Remember, you can add R's, but you cannot add U's. Remember that heat always flows from higher to lower temperature unless we force it to do otherwise. And that heat movement increases with increased area, increased time, increased delta T, and the increased U value. And finally, that if you want to calculate the heat movement per hour, it's just UA delta T. Okay, so in this lesson, again, what we did was we looked over what a building envelope and conditioned space is. We looked at how heat is transmitted through a surface and how to calculate that heat movement.